So here's another example where it asks us to solve the system of equations graphically. So we would want to make sure that both equations are in slope-intercept form, which they are. The y's by themselves. So for the first equation, I'll graph in red. We have a slope of 1 and a y-intercept, a b, of 6.1. Well, 6.1, okay, so we know that would be really, really close to 6, but maybe a little bit above. So I'm going to plot a point right above the 6. And a slope of 1 over 1. Well, I'm going to have to be careful because now I have to go slightly above every single point, slightly above there. I'm hoping I'm about right, and I have to make sure when I go that way, I'm above slightly, and I can represent my line that way. Okay, that would be the first one. And the second one, again in slope-intercept form, we can see the slope of -2, but we see now a y-intercept of -1.4. So -1.4, I'm definitely going down to -1, but maybe halfway between the boxes I can approximate. And then I have to go down 2 and right 1, but I'm already losing sight. Okay, 2 from 1.4, -1.4 on negative, so that would be, and then 2.4, so, and I'm not even sure, maybe somewhere around here, and down 2 again, maybe somewhere here, and maybe I gotta go up 2, so somewhere here, somewhere there, maybe. I'm not sure. I'm actually losing it with my lines, and if I create my line, they're going to intersect somewhere, maybe this point, and I'm not exactly sure. Maybe it's -3. I can't even tell for sure. So it becomes very, very difficult. Why is it so difficult to solve this system by graphing? I can't even come up with a 100% correct answer graphically. Well, look at our two equations. It's definitely the y-intercepts. Those decimals, and then moving with our slope from a decimal, it's very easy to get lost with movement of points. I'm not even 100% sure I'm graphing a decimal correctly. I'm estimating. So there has to be a different way to find out exactly what that point is. So when graphing is inefficient, or you have to be approximating with it, there's another way to solve a system, and it's known as substitution. Substitution allows us to create a one variable equation out of two. So the 3 steps for substitution is that first, you have to have a variable by itself. If you are not given a variable already alone, you have to find the easiest variable to solve for or get it alone. Then, step 2, you can substitute that expression into the other equation and solve for the variable. For step 3, substituting that numerical value you found into either equation and solving for the other variable to get that point as a solution, or x comma y. Now this sounds difficult, so let's see it in action with 2 examples. So let's solve this system we were trying to graph using substitution now instead. So step 1 is to choose an equation from the system and substitute it into the other equation. In other words, we want to make sure our equation is alone. So the first equation has the y by itself, so we're going to substitute it into the second equation. So x plus 6.1 is going in for the y in the second equation, which creates the now one variable equation, x plus 6.1 equals -2x minus 1.4. We can now solve this new equation. We'll add 2x to both sides. 1x plus 2x is 3x, plus 6.1 equals -1.4. We'll then subtract 6.1 from both sides, creating 3x equals -7.5. We'll divide by 3 to get our first value, half of our answer, x equals -2.5. So this is the value of x for our solution. Now we have to find the value for y. So we're going to substitute that solution, the x equals negative 2.5, into either equation and solve for y. So this is showing you it substituted into both equations, into the first one and into the second one. You don't have to do both, but let's see that we get the same answer of 3.6 if we chose either equation for y. So that means the solution to this system is negative 2.5 comma 3.6. Again, we only had to plug the x value into one of these equations to get this. The second one is more of a check. You could do it. It's not going to hurt, but it's just going to take a little more time. The answer should be the same for both, though. You should have the same y value for both. After you evaluate this for the solution, it's good practice to double check your work by then substituting that point into both equations. So if we want to check to see if our answer, negative 2.5 comma 3.6, satisfies both equations, we'll take x as negative 2.5 and substitute that in for x. And we'll take y as 3.6 and substitute that in for y in both equations. When we make our substitutions and simplify down, it does make both equations true. 3.6 equals 3.6 in both cases. So that means the solution is correct. Let's look at one more example for substitution. Now let's solve this system. 2x minus 3y equals negative 1 and y equals x minus 1. So the first step is to substitute one equation into the other equation. Now, since one equation, this second one, y equals x minus 1, is already solved for y, that's what we're going to substitute. We're going to take x minus 1, what y equals, and substitute that into y in the other equation. Think of it like a substitute teacher. The y is now gone, the regular teacher's out, and its substitute x minus 1 is in its place. So our new equation is 2x minus 3 now times x minus 1 equals negative 1. So we can now solve the new equation. We'll distribute the negative 3, making 2x minus 3x plus 3 equals negative 1. 2x minus 3x is negative x plus 3 equals negative 1. Subtract 3 makes negative x equal negative 4. And divide by negative 1 is where they're then getting x equals 4. Once we have x, we can then substitute the solution into either equation and solve. So if you substitute it into the first equation for x equals 4 here, you get 8 minus 3y equals negative 9. Divide both sides by negative 3 after subtracting 8. And you get y equals 3. If you did it in the second equation here, 4 minus 1 is 3. Now, you could use either equation, but notice the second equation was a lot shorter. You only had to make one small operation, and you got y equals 3. So either will work, but it becomes clear that one of them is easier to solve for since it was set up the equation for y. So x equals 4, we see y equals 3. So together our solution is 4 comma 3. If we do our check where x equals 4 and y equals 3, and we substitute that into the first equation, we substitute that in x and y into the second equation, we can see that it creates true statements for both. So therefore that ordered pair satisfies both, and that official solution is now 4, 3. So substitution is a way to get your answer without graphing, especially because we see graphing that has limitations. So it depends. It could be, you have to be really good at solving equations in order to do this, because it carries through solving for x, solving for y, simplifying, but it is an alternate way to solve a system, especially when graphing fails us. Choosing a variable. Sometimes a variable is not already isolated. When this occurs, you need to determine which one you would prefer to isolate and finish solving the system with the substitution method. So let's examine each of the equations below. We have to ask ourselves, Which variable would you choose to substitute and why? And there's not a right or wrong answer here. It's just what you see when you're looking at the equations. And then there are certain tips and tricks that you can use. So for example, the first system, both equations have a variable isolated. So in this case, it doesn't really matter which one you would prefer to choose. You don't need to isolate either. So you can choose to substitute either in. Now, the second equation doesn't have the decimal to work with. So if I choose to substitute that into the other, I might not have to work with decimals as much, or I might not have to distribute. So the second equation might be a little nicer to work with substituting into the other, so you wouldn't have to work with the decimal. In the second system, we now have both equations where a variable is isolated. But the second equation, I'm noticing that the x variable is almost by itself. All we would have to do is add 4y to both sides, and that would isolate the variable x to equal 4y plus 1. In one step, you have the variable by itself. In the other equation, you would have to subtract 4x and divide by a negative, and then dividing by a negative can always be tricky, so you want to be careful there. So we would probably be best to choose the second equation again in the second system. Now in the third system, both equations don't have a variable isolated, and they're going to be both multi-step because they both have coefficients here. Now the first equation doesn't have negative coefficients where the second one does, so that might be an easier one to work with. Again, there's no right or wrong answers. It's just what you think is going to be the easiest for you to work with. Usually it's if there's just one step to get the variable alone, or you want to avoid working with negatives or decimals. But anyone can work. It's just what you will have the easiest for you, what's going to make it the best choice to get to your answer. Here's an example of solving a system using substitution. The system is x plus y equals 6 and 5x plus 5y equals 10. So first, we're going to solve the first equation for x. Since looking at the 2, that would be one of our easiest options to get a variable alone, since it's not automatically alone now. So we'll subtract y from both sides, making it x equals 6 minus y. We're then going to substitute 6 minus y into x of the other equation. So it's no longer 5x, but 5 times 6 minus y plus 5y equals 10. After distributing, that would give us 30 minus 5y plus 5y equals 10. And negative 5y plus 5y is going to simplify to 0 or cancel out, leaving us with 30 equals 10. This is definitely false. So since 30 equals 10 is a false statement, the system has no solution. We can't solve for a variable. Our answer then just becomes no solution. So when your variables cancel out, when you're trying to solve using substitution and you end up with a false statement, we can always conclude the answer will be no solution. Let's look at this example now and see what happens. Again, we're going to solve the following system trying to use substitution. So x plus 4y equals negative 3 and 2x plus 8y equals negative 6. Now looking at this, the first equation solving for x would be the easiest, fastest way to get a variable by itself. So we'll subtract 4y from both sides and get x equals negative 3 minus 4y. We'll substitute that into x in the second equation, making it 2 times the quantity now, negative 3 minus 4y, plus 8y equals negative 6. We'll distribute to get negative 6 minus 8y plus 8y equals negative 6. and negative 8y plus 8y is going to simplify to 0, cancel out, leaving us with negative 6 equals negative 6. This is always true. Negative 6 does equal negative 6. So now, since negative 6 equals negative 6 is always a true statement, there are infinitely many solutions to the system. So we can conclude anytime the variable disappears or cancels out and we're left with a true statement, it would always now the answer be infinitely many solutions. We now have these two special cases when trying to solve for substitution.